Okay, so let's come back to again our discussion on solutions of linear state space equations. So again we will start with x dot equal to a x. For the moment we will leave out the input term and define slowly the concept of a state transition matrix. So it essentially tells me how a state goes from a certain x at time t equal to 0 to any x at some time t. So given an initial state, how can I compute the state at some future time t? Essentially, like I am looking again at solutions of the differential equation. So let me first define an equivalent matrix differential equation. So this was my vector differential equation where, because x was in Rn. So this is a matrix differential equation, right, where m dot is a m t, a is again n cross n matrix, and m is also now has a matrix representation. Okay, it will slowly be clear why I am doing this, and we will derive this a little later, but for the moment we will just learn it a little not very constructively, but something which will help us understand understand the basics of state transition matrix. Okay, so let me start with this matrix differential equation. Okay, and let me define as phi t comma t naught as the solution to this matrix differential equation with the initial condition being the identity. Okay, so I am just using any arbitrary time as my initial condition, even though t naught can also be equal to 0. So we will alternatively use this to make computations easy, where in many cases I will call, or I will assume that t naught is actually equal to 0, even though nothing changes in generality. Okay, so this matrix phi is called the state transition matrix. Okay, now if this is the state transition matrix, so what I claim here, which I will prove, is that the solution to x dot equal to a x, okay, the b goes away here, right. The solution to x dot equal to a x is simply given by this one, x t is phi t comma t naught x naught. Okay, now this is a matrix, right. So phi t comma t naught is a matrix, which is the solution to this matrix differential equation, and just multiplied by the initial state. Okay, so let us try and prove this one. So again, so I start with x dot is a x, and what I claim is that this is further the solution to x dot equal to a x is given by x t is phi t comma t naught x naught. Okay, so let's for simplicity assume that t naught equal to 0, even though nothing changes with this. Just my expressions just look a little easy. Okay, so what is the property of the state transition matrix, or how did I define this? Well, this was the first thing, right? Phi t naught comma t naught was the identity, or the initial condition of the matrix differential equation was the n cross n identity matrix. Okay, now what I claim is that the solution to x dot equal to a x is the solution to x dot equal to a x is just this expression here. Okay, so how do I verify this? Okay, first is check the initial conditions. Okay, what is the initial condition for this, for the original differential equation, that x at 0 was x naught. Okay, now I will just do this, right. So this is the solution which I propose, right. X of t is phi t t comma t naught, I will just say phi t naught is 0, so I will just omit that, times x of 0. Okay, now what is the, let me verify the initial condition. Okay, x of t is phi at 0 times x at 0. So what is phi at 0 is the identity. So this is x, sorry, I should write as x at 0 here, sorry, this x of 0, this is to verify the initial condition, is phi of 0 times x naught. So, what phi of 0 is the identity, and therefore, I retain the initial condition. Okay. Now, second thing to verify is if a certain x of t is a solution to x naught equal to x, then it must actually satisfy the differential equation, right. That is what we learn as a trick of backward substitution when I am maybe writing a competitive exam. I do not really compute the solutions, but I actually check if the solution satisfies the original differential equation, right. Okay. So, let me do what is x dot t here. X dot t is phi dot of t, I will just again assume that t naught equal to 0. Okay. Now, where does phi dot t come from? Well, phi dot t, so is the solution to this matrix differential equation, which means phi dot is such that it satisfies A times phi of t x naught. Okay. Now, what is phi of t x naught? Phi of t x naught is exactly this. This is A times x of t. Okay. So, I recover starting from this solution, which I rewrite for t naught equal to 0 as phi t times x naught. I start from this differential equation, I substitute this solution which I propose for x dot equal to a x, I substitute for x equal to here, and I recover again the original differential equation. So, the initial conditions agree, and also the differential equation agrees, it satisfies. So, this function which I propose as a solution satisfies the initial condition, and it also satisfies the differential equation, right. And therefore, well, this is the, so this statement is true, right, that the solution to x dot equal to a x is given by x of t is phi t t naught x naught, right. So, it also a little goes on to say, or what we use here, right, that if two functions of time, they satisfy the same initial conditions and the same differential equations, then these functions are equal, right. So, that is what I make use of, or which is kind of in a way obvious. And what is a little key here, which is not explicitly discussed when we do our basic state space representation in control 1, is that solutions to a given differential equation exist and they are unique. Essentially means given an initial condition, I can only travel in one particular direction. There will be only one solution, or that I stand here and I can go this way, up, down, all those are not allowed, right. So, so there are some conditions which guarantee existence and uniqueness of solutions to differential equations. We will not do the details of that, but for our course we will assume, it is not assumption, right, it is actually true that solutions will exist and they will be unique. So, by uniqueness it means given an initial condition, there will be only one solution that will emerge out of that initial condition. So, if I were just to draw a trajectory, say this is x naught and the solution goes this way, this is the only possible one. There will be nothing which goes maybe this way or even this way. Okay. So, existence and uniqueness is okay, this is guaranteed, but we will not really go into the details of that. Okay. The second thing which we can prove is the following, right. So, x, so let me write this down, is phi t comma t naught is phi t comma t1 phi t1 comma t naught. Okay. So, again phi is a solution. So, let us just check if the left hand side and right hand side do they satisfy the same initial conditions and they satisfy the same differential equations, and then I exploit this statement, right. So, if two functions satisfy the same initial condition and the same differential equations, then essentially the functions are equal. Okay. So, in the left hand side I have the following. So, I know this already, right, phi dot t comma t0 is a phi t comma t0. Okay. So, first check for any initial condition, right, or just check for any value of time t if they agree. So, let me check at phi, say at t equal to t1. At t equal to t1, on the left hand side I have phi t1 comma t naught, on the right hand side what I have phi T1 comma T1 phi T1 comma T naught. Now, what is phi T1 T1? This is the identity, and therefore, well, they both agree at point T1. So, let me assume that as my as a condition where I am checking if they are equal or not. Okay. Now, do they satisfy the same differential equation? Well, I know already this, right, that phi dot is A times phi. Now, let us look at the on the right hand side. On the right hand side, well, if I differentiate this, well, this is all these are constants because I can compute them at T1 and T0. So, this is the time varying term. So, I have phi dot T comma T1 phi T1 comma T naught. Okay, now what is phi dot? Phi dot is A phi T comma T1 phi T1 comma T naught. So, these two functions satisfy the same differential equation. So, such that I have on the left hand side I just differentiate this function. So, I just write this, right. So, d by dt of this entire thing here, right, phi T comma T1 phi T1 comma T0 will give me A times the entire function rewritten here itself. Okay. So, the second thing is also true, and I think well, this can be a little easy to prove, right. So, I will just leave that as a little exercise, right. Okay. So, let us spend some time just solving a particular thing, right. So, again unforced system. So, u goes to 0. Then I have that the system matrix is of this form. So, okay, just before this, right. So, why am I writing this in a little more generality is because okay, like this notations can also be used when I am using a time varying system for example. And for now it must be little easier to guess the following, that in the case of a LTI case, this is my state transition matrix starting from time t equal to 0 and at any time t, and because again the solution, if you look at it, so what I call, right. So, the solution to x dot equal to a x plus b u or without the input is given by phi of t, let us assume t naught equal to 0 x naught. So, what is phi of t? Phi of t is e power a t x naught. It also satisfies the property that this initial condition is the identity. Just put t equal to 0 here and you get the identity. For if it just for any arbitrary t comma t naught, you will have things like this, e power a t minus t naught. That satisfies that at t equal to 0, this initial condition is the identity. So, a little so this is an easy to guess starting from here, right, that e power a t is essentially the state transition matrix for a linear time invariant system of the form x dot equal to a x plus b u. Okay. So, let us see how to compute this. Well, I have given two differential equations with certain initial conditions. System matrix is like this, and I just do this way, right. So, I just expand it in powers of a and I do all the complex math, and I can conclude that this is the solution, e power minus 2t, because this has the form of e power minus 2t, 0 here and so on and so forth. Okay. Now, do I really do this all the time, right? I just give me any matrix, should I expand it in powers of t and a and then try to get a solution, right. So, that might be a little tedious, but what we know, which we already started motivating with, is the use of Laplace transforms. Now, that makes life much easier for me, right. So, if I have a general state space representation x dot equal to a x, the state transition matrix. Okay. So, let us see how it goes, right. So, I have x of s as s I minus a inverse x naught. This s I minus a is always invertible, and I think we should remember this from our basic control course. If not, just let me know, I can do maybe proof of that in the forum. But very important thing to understand here is that s I minus a is always invertible. Okay. So, once I know this, if I write this in the time domain, well, this essentially the inverse Laplace of Si minus A inverse is essentially my state transition matrix, which also takes this form e power at, right. Okay, and then I can do the entire stuff again, and it actually becomes a little easier, right. So, I can, so given transfer function kind of thing here, I can always rewrite it in this time domain via the inverse Laplace transform. I do not need to teach you this. This has been done in control 1, also some basic courses on differential equations. Okay. Some little properties. Well, at t equal to 0 is of course identity. This, well, all this I think these are easy to prove, right. E power at is e power minus at, the whole of inverse. This is also easy to prove, e power at1 plus t2 is e power at1, e power at2. This look like those lots of indices which we study in high school. Okay, this I will leave for you to derive by yourself, that e power a1 plus a2 times t is e power a1 t times e power a2 t if and only if the matrices commute, that a1 times a2 is a2 times a1. And lastly, okay, d by dt of e power at is this one, and this is also equal to e power at times a. And lastly, with the integral version of a. Okay, now this the scalar case is actually obvious to like relate. So, in general, well, if I am also talking of a time varying case or whatever, I will just have, instead of e power at, I will just have some state transition matrix which is called phi of t, which has its own set of properties. Now, a couple of them we already derived over here, over here. So, in general, what will the state transition matrix satisfy? Okay. So, just these are the properties, but and you can relate them to each time to the special case of state transition matrix, which is e power at. Okay. So, phi of 0 equal to 1, what does it mean? That the state response at time t equal to 0 is equal to the initial condition. So, if I start at t equal to 0 and I measure at t equal to 0, I will always be at that same point. So, so the transition is just the identity, like what takes me from x at t equal to 0 to x at t equal to 0, that is the identity. Okay. Now, phi of minus t is simply the phi inverse of t. Physically, what does it mean? This is the response of an unforced system before time t equal to 0 may be calculated, and this can actually be calculated from the initial conditions, because what is my solution? Solution I always wrote in terms of phi of t, x of t is phi of t, assuming that the initial time is 0 times x at 0. Okay. Now, I just look at what is x at minus t, this is simply phi at minus t times x 0, and this is phi inverse of t x 0, right. Okay, assuming that we could actually derive this thing. Okay, it also in some way resembles this one. So, I will just leave that for you to derive. It's again in the same steps as what we did in the first two lines of or proving the first two statements. Okay, and phi inverse always exists. Again, I do not need to prove why that is true, but it is kind of obvious from the statements that we have made since the beginning of this lecture. And similarly, phi of t1, phi of t2 is phi of t1 plus t2. Okay. This also you can prove fairly easily. Okay, what does this property tell me? With this property, the state response at any time t may be defined from the system state specified at some other time than t0. For example, if okay, I do not know what is the state at time t equal to 0, but I know at some t equal to t naught. Okay. So, how do I find that? So I do not know this information, right. I do not know what is x at t naught, but I would want to, but I know what is x at some arbitrary time t naught. Okay. So, I just use the properties which I know earlier. So, phi of t, I can write it this way. Okay. And then I can use this property to rewrite. Okay. So, I can use the second property to rewrite it in this way, and then the third property will just plug in here as phi of t minus t naught times x of t naught. Okay. So, just rewriting the first two properties and then making use of this. So, with this property again I repeat that if I do not know what is x at t equal to 0, but I know something at x equal x, the value of x at some time t naught, can I still compute x of t? Well, the answer is yes, and I just make use of a property which kind of beautifully looks like this. Okay, so that concludes the lecture 1, where we started off with scalar differential equations, unforced and saw the unforced response and generalized that to an n-dimensional state space system, and defined the concept of a state transition matrix and listed out few properties which will be useful for us. Okay, one thing before I conclude is the following, right. So what we did in some of our previous lectures was about the diagonalization, right. Of a matrix. Okay. So, let us say I am given a matrix A which looks like this, lambda 1, 0, 0, lambda 2. Okay. It is easy to verify that e power a t in this case is simply a matrix which looks like this, e power lambda 1 t, 0, 0, e power lambda 2 t. Okay. Now, I know that if A is not in a diagonal form, I can convert it into a diagonal form, A into a diagonal form. Okay. Now, let us say I can convert, say x equal to p times c. So, x dot is A x, p z dot, this is A x, sorry, A times x is p z dot, I just do p inverse A p times x is z. Now, I know that I can convert this into a diagonal form. Okay. Now, let me call this D. Okay. This D is P inverse A P, okay, and I wish to find what is e power A T, okay, or in other words I can also write A as P D P inverse, where D is a diagonal matrix. Okay. Now, it turns out, okay, this is a little proof, actually a small proof, e power A T is P e power d t, which is easy for me to prove or easy for me to compute, times P inverse. Okay. So, this is actually a more computationally efficient way of computing e power A T via the diagonalization. Okay, this actually will be a z here. Okay, so let us see if we can actually prove this. So, I know that x of t is e power A T x x of 0. Okay. So, what is z of t, what is the relation between z of t and x of t? I know that z of t can be written as in terms of x as, so this is z is p inverse x. So, I have p inverse x of t is on the right hand side, I have e power dt. What is z naught? Z naught is p inverse of x naught, coming again from here. So, this implies that x of t is p e power dt p inverse x naught, sorry. Yes, right. So, this is p e power dt p inverse x naught. Okay. So this is a little proof of how I can compute e power at when I know that I can diagonalize the matrix. Similar expressions also exist when I have when I cannot diagonalize the A matrix, but I have the equivalent Jordan form of the A matrix. So that was a little illustration of why the kind of tools we learned in the previous two weeks of lectures were actually useful. So we will in the next lecture do solutions to equations which have input in them, or we will look at, in other words, force response of scalar LTI systems, and then we go to n dimensional systems, and also have a little bit of introduction to discrete time systems. So that's coming up shortly. Thank you.